Okay, in my previous classes, I have already mentioned about the basic topics about cryptography. So, as we mentioned that the main topic known as cryptology, and it has two branches. One is constructive one, that is known as cryptography, and another one is the destructive one, that is known as cryptanalysis. So, while dealing with cryptography, we basically encounter with two major topics. One is symmetric key cryptography, another one is asymmetric key cryptography. So it depends, these two terms or these two topics actually depends on these keys. So in my previous classes, I have already talked about these keys. If these two keys are happen to be the same, then we call it symmetric key. Another name is private key cryptography. Whereas if these two keys are different, then the scheme is known as asymmetric key or public key crypto system. So in our syllabus, we will have both. So initially, I will start with few symmetric key crypto systems which are historically quite important. So in my last two classes, I have already described about them. For example, Caesarian cipher or SIP cipher, then substitution cipher, then affine cipher, then Hill cipher, then Vigenère cipher, etc. So all of them, they are basically examples of this symmetric key crypto system. So that means both sender and the receiver, they are going to use the same key. So in this class, what I'm going to decide that I am going to give you few basic ideas about the preliminary mathematics. So in my two classes, some of you might have missed the part of what is group, ring, field, etc. So what I have decided that in this class, I'm just going to give you a brief idea that will be required for most of you during my whole course. So for if you are from mathematics background, then this class seems to you quite easy to you. But if you are not from mathematics background, then this course or this class, you may find it quite interesting. Okay. So let us try to explain what is group, ring, and field. But before going to that, let us try to have some basic idea. Okay. Suppose I want an some calculation word. Say I call it say W. W consists of some elements. I don't know what are these elements. Something is there within this W. And if I ask you the question that what kind of operations, especially say in case of your cryptography, what kind of basic operations that you can think of? So a natural answer would be I can think of addition, I can think of subtraction, I can think of multiplication, and I can think of division. So mostly they could be thought of as my basic operations. For example, this W may be my real numbers, set of all real numbers. Okay. So there from our childhood, we have already started addition, maybe for integers initially, and then from real numbers, afterwards some rational numbers, maybe after that, maybe some irrational numbers and all. Okay. So when we talk about this addition, so if W is my world of all calculations or elements on which I'm going to apply this plus, minus, dot, and it could be any arbitrary operation, okay, star maybe. So when we think about this addition, simply for example, I have only one operation, for example, plus. So the best thing that we should think of is that if I add any two elements from that W, it should not go out of W. That means it should be within W. If it goes out of W, then you can understand that always you have to have a check that whether this addition is within W or not. But if by some means, if you have some property of W which can ensure you that, okay, do not worry about that, whatever be the elements you take from W, and if you add them up, then that will always be within W. If that could be a case, then suddenly your confidence will be extended. As a result, you do not have to think about whether addition of this is going out of your range or not. Okay, that property intuitively known as closure property. Closure closure property. Okay. So what I say that this property is known as closure property. That means where you do not have to worry about whether addition of two elements is going out of the business or not. For example, let us think about say Z. Z means set of all integers. Set of all integers. Okay. And if I consider this to be plus, then if I ask you this question, take any two integer, will you be able to go out of the range of W? You cannot go out of the W. Okay. If I consider say minus as well, and if I ask you the question, if you subtract any one element from other, will you go out of the range? Certainly not. You will always be there. Similarly, if you consider, if I multiply any two elements within Z, then will it be within Z? Of course, the answer will be yes. If you consider any two elements from Z, then suddenly the product of these two elements will also be within Z. But the problem comes for the first time is here. For example, if I divide say 11 divided by 2, then suddenly this answer will not be within Z. So you understand that with respect to this, and this closure property is satisfied. But with respect to this, the closure property is not satisfied. Okay. So that is very important aspect. Now, if you have only one operation, for example, if I start with n, that means set of all natural numbers, set of all natural number, okay, natural numbers. That means few of the authors they start with 0 and few of the authors they start with 1, 2, etc. That means set of all positive integers. Few of the authors they include 0 within this set of natural numbers. It depends. So for my case, I assume that n means set of all positive integers. That means 1, 2, etc. Okay. And if I consider n with respect to addition, then suddenly it will satisfy the closure property. Closure property with respect to addition is done. If I consider multiplication, then closure property is done. But if I consider subtraction, will it satisfy the closure property? What would be the case? If I
No, sir.
consider yes or no?
No, sir. Not.
No, sir.
No, because if I consider 2 minus 3, then suddenly the answer will be minus 1, and that is suddenly not within n. So it is not satisfied. Similarly, in case of division as well, it will not satisfy. Okay. So if I have only one operation, then this operation and this set is very important. That means I must have some algebraic operation on which if I have only one operation, then that set should be such that it should satisfy the closure property, and that will in turn give us the confidence that whatever you will do with that operation, that will always be within that set. So closure property is very important. Okay. Secondly, if I come here, sometimes we require say A plus B plus C. Suppose I have a set W on which I have some operation W plus. Okay. So I know that plus D, and I always know that A plus B plus C plus D is always same. But if I started doing some bracketing like this, and if I ask you the same question, will that be same? That means when you are doing some calculation, do we really bother about this brackets, or wherever you need, you can put a bracket if it is only one operation. So you can see that in case of addition, and if I consider this to be Z, and if I consider this is to be addition, then we do not have to worry about. But we must worry about in this case, say for example, everywhere is minus, and we know that this is also minus, same as minus b minus c minus d. But if we have this and if I have this, will that be the same meaning as this? Do you think that that will give you the same meaning? It's certainly not. Okay, that means here you cannot shift or switch the brackets wherever you like. But if this be the case, then you are really very happy because you do not have to worry about the brackets with one operation. You can shift the brackets wherever you require and in whatsoever manner. It won't be a problem. So that property, if you have this property, then this property is known as associative property. Associative property. Okay. Now think about a thing like in your W and maybe your star, you have some element, say E is some alphabet or some element from W. It has a special property like whatever may be the element from W, if you A star E equal to E star A equal to your A, that means it will always give you back that element from left or right, wherever you can compose with it or you do a kind of this kind of operation over it, it will give you, and that is true for all. It's not with for a particular element A, but if it is for all A belongs to W, then this E has some special meaning, and we call this E as the identity element. Identity element. Okay, so that is also very important. Another is very important. For example, if you have this like this, and if you take an element A belongs to W in such a way that A star A dash, or in we call it A inverse, that means for each A, for each A in mathematics, for each and for all, they are very very important terms. Okay, for all means it should be true for all elements, and for each means it has to be true for each of the elements. Okay, they sounds almost same, but many places you may find that for all and for each there might be some difference. It says that for all A, that single element will be sufficient, but it says that for each A there will be an element A inverse such that this property is satisfied. A inverse star A, that should be equal to E. Then we called this particular element as the inverse of A. Inverse of A. Okay, it says that for each element I must have some element A dash maybe, or I write it this symbol A to the power minus 1, such that if I make a composition of these two elements, then that will certainly give me the element E, where E is the identity element. So all these properties are very important. For example, when we talk about R, so if I consider R, and if I have only one element plus, then you can understand that all the properties that I talked about, that means you cannot go out of the range of R by adding two elements of R. That means if I add two elements, two real numbers, you will always be within R for all AB belongs to R. Similarly, this property is also satisfied, associative property. A plus B plus C for all A, B, C belongs to R. So 0 belongs to R is the identity element. Is the identity element. Why? As if you add any number with 0, then you will always get back that number. Okay? For all A belongs to R. Similarly, if you take any element A belongs to R, what will be the inverse of A? Can anybody tell me what would be the inverse of A?
minus.
Very good. So if you take A belongs to R, then suddenly minus A is also belongs to R, and A plus, if I consider minus A, that should be equal to minus A plus A equal to 0 for all A belongs to R. So all the four properties that just now I have mentioned are satisfied here, and this property is known as closure property. This is known as associative property, associative property. This is known as identity, and this is known as inverse. So all the basic properties are being satisfied here. Okay. Now the question is, if I have more than two operations, for example, I need some W plus and say dot. And I also want almost everything. That means I also want like it should be the plus and dot should be must satisfy the closure property. There must be some identity element. The associative property must also be satisfied with respect to both plus and W, and all the properties except for one property, that W with respect to dot. In this case, I need only inverse for, I need inverse for all elements in W minus the identity element. So I just make a one restriction here. So as you understand that if this is satisfied for all the four properties are satisfied for this, then this should be a group. Okay. Now, if this is satisfied, almost all the properties are satisfied except for identity elements, except for the identity of the zero element of W, I just remove this, and for remaining all the elements, if the W has also the multiplicative inverse, then it will have some special name. For example, if I consider simply R plus and dot, then you can understand that you can do almost all the properties, you can exploit all the properties with respect to this R and plus, and then R minus 0 and dot. Okay. So also there is some relation between this. Okay. For example, if I multiply like 2 plus 3, then what it looks like, it should look like 2 into 3 plus 2 in, sorry, 2 into 2, it should look like 2 into 2 plus 2 into 3. Okay. So this property, that means it gives a kind of relation between plus and dot. So this is plus and this is dot. And this distribution property actually giving you an idea how this element should distribute over plus from left. Similarly, if I take this and if I consider, say, multiplied by 3, then it should look like 2 plus 3 into 3 into 3. So this is the distribution of dot over plus from the right. So these two properties are called left and right distribution property. Okay. So they are called left and right distribution property. Okay. So as a whole, what you get, if you have more than say W plus and say dot, so here we have more than two operations, then if you want to be very comfortable, then this plus and dot, they must satisfy like the associative property, closure property, also the distributive property, as well as the with respect to this some identity property, with respect to this some identity property, and so on. So these altogether gives you the basic motivation why we should study the group, ring, as well as field. So in this class, I will first start with what is a group. And the history is quite amazing. Okay, so initially when the group started, the concept of group actually came quite late. So first I will give the definition of a group, then you will understand that this definition, we call it axiometric definition. This definition came quite late. But before that, the formation of the properties of group actually took place long back. Okay. So what is group then? So for to have a group, we must have two components. For example, a non-empty set along with a binary composition. So this is said to be a group, to be a group where G is a non-empty set and star is a binary operation. Okay. So let me first highlight satisfying. Okay, let me first write out the definition. Binary operation on G satisfying the following properties. One, associative. Two, existence of identity. And three, inverse. Now you may ask you the question, why did I miss the closure
Closure.
property? Closure property. Okay. Many of the books, they also include the closure property. But as I mentioned, the definition should be very sleek. Okay. You should not repeat the same property twice in a definition. So definition should be very sleek and smart. Okay. So here I have mentioned what is a binary operation then. So here I have already mentioned that star is a binary operation. So if I ask you what is a binary operation on G, it means it's a mapping from G cross G to G. So if I ask you the question, when you are going to add numbers, how many minimum numbers you may require? It may be same, but you cannot add just one number. So if I give you one and if I ask you add one, thus the question would be add with whom? Okay, it may be add with one, add with two and something. So for addition, you at least require two numbers, right? So this addition may be thought of as a function. From where? From, if I consider addition within elements of real numbers, then we can think of addition as a function from R cross R to R. So how the function is then defined? The function is like this, plus of 2, say if it is 1 plus 2, then 1 comma 2, and it gives you the value 3. Now look at this. This belongs to R. This belongs to R. That means this tuple belongs to R cross R. Okay. So class is just like a function, like our f is a mapping from A to B. Where it sends, it takes as an argument some element of A, and that goes to some element of B. That means ultimately this FA belongs to B. So if I consider this to be a function, then f of or plus of 1 comma 2, that gives 3, and that 3 goes to this R. So you can understand this belongs to R. So binary composition or function is a mapping from R cross R to R, or in general here we consider star. So star is a mapping from G cross G to G. Now, since this is a mapping, from the definition of mapping, you cannot go out of B. So, for example, if I consider a mapping from A to B, then FA can never go out of B, right? Because it's a, so you know the codomain or range. So, this FA cannot go out of the concept of B. Since plus is a mapping from R cross R to R, after doing this addition, this resultant number like 3 cannot go out of the range R. As a result, if I mention that star is a binary operation, then the concept of closure is not required because that is already mentioned within that definition. But unfortunately, few of the books they consider this along with these four properties. So, but the correct option would be, or the correct way of writing it formally in a smart and sleek way would be, if you consider this to be a binary operation, then you do not need to mention the closure property because the closure property is automatically taken care of by this term binary operation. Is it clear to all of you? Any question? If you have, please let me know.
No, sir.
Okay. So all the four properties are very important to give you a kind of freedom to work with numbers or to work with some elements of a particular set. That's why we consider if we have uh, only one operation, then the best thing that we can think of this structure should be a group structure. For example, when we consider say plus, I want to my operation is my say star. So if we take G and star together, then we are quite safe being all these properties are satisfied. So all these properties gives you lot of uh, freedom to work with the elements with G by using this operation star. That's why we usually take group. Okay. Now when we talk about group, let us have some few examples. Okay. So the best thing already we have talked about is R plus is a group because it satisfies all the properties. Set of all rational numbers with respect to dot is a group. Now if I consider set of all irrational numbers with respect to addition, will that be a group? I is irrational number. So collection of all irrational numbers. For example, root 2, root 3, root 5 and so on. This collection. Will that be a group with respect to addition? Okay. First, if you add any two of the irrational number, will that be a closed with respect to that? If we consider root 2 plus root 3, will that be a rational number?
No, sir.
So it will be always irrational, right? Okay. So, but since, okay, let me check. Then if I consider associativity, say root 5, will that be same as say root 2 plus root 3 plus root 5? Will it satisfy? Will that value be same? True or false? Will that value be same?
Yes, sir.
Yes, so that is true. Now the identity element. So what do you think that that should be an identity element so that root 2 plus e should be equal to e plus root 2 and that should also return you back root 2. So what should be the value of e?
1 by root 2.
If I add
0.
1 by yes, it should be 0. But do you think that 0 is an irrational number?
No.
So 0 is a rational number. So 0 is not within this. Not only that, as I mentioned, if I do just additive in that way, positive sense, for example, since root 2 is there, minus root 2 must be there if I consider addition because its inverse should also be there. And if you add them up, then also you will get 0. Okay. So 0 is not within that set, irrational number. So in many ways, you can say that the set of all irrational numbers will not be a group because it fails to be having the identity element. Also, if you consider the okay that way, I mean it cannot be having 0. So in that way, it cannot be closure property. So if you consider this to be A and this to be B, and then if I consider B plus A, then that becomes 0, and that is not within that range of irrational number. So in that way, this is also not a group. Okay. So let me have some more examples. Most natural examples for group is Z plus, set of all integers with respect to plus, and that forms a group, no doubt about that. Now, if I consider 2Z plus dot, will that be a group? 2Z plus dot, true or false? What do you think? 2Z plus dot? Consider any two even numbers. If you add them up, that will always be an even number, right? So closure property is satisfied. So if you have 2a plus 2b plus 2c and 2a plus 2b plus 2c, then you can suddenly switch or interchange the brackets, no problem. 0 is an even number. So you can think of 0 as an identity element. Also, if you consider, say, any number, say 4, then what would be its inverse? What would be the inverse of 4?
-4.
-4.
Minus 4 is the inverse of 4, and that is also an even number. So that is within this 2Z. So all the properties of groups are satisfied for 2Z as well. Okay. So 2Z is also. So in particular, you can write NZ plus, where n equal to 0, 1, 2, etc. If I put n equal to 0, then the group becomes 0. If I put n equal to 1, then the group becomes Z. If I put n equal to 2, then it comes 2Z and so on. So all of them, they form the groups, okay, with respect to addition and so on. Okay. Now if I consider, say, Z with respect to multiplication, will that be a group? Is it a group? What is your conclusion? True or false? True or false?
True. True.
True. Why true?
Sir,
If you can,
false.
okay, why false?
So 0 identity is 1. So
Okay, yes, what is the problem then?
no, nothing, sir. But
So line by line, let us try to. If I multiply two integers, then that would be an integer, no problem. We can switch the brackets, no problem. One is the identity element, that is also not a problem. But what would be the inverse of 2?
Inverse. It's an
Yes.
inverse.
So
Property
what
will
would be
not be
the,
satisfied.
yes, so the inverse of 2 should be half to maintain, like 2 into half equal to 1, which was already an identity element. But unfortunately, half is not within Z. So you cannot have multiplicative inverse of 2 in Z. As a result, this is false. Okay. Now let us consider this set of all rational numbers. Let's start with positive rational numbers with respect to multiplication. So this is set of all positive rational numbers. Okay, and then this is simple, the normal multiplication. Is q plus with respect to multiplication a group? True or false?
Sir, I think false.
Okay, why?
Sir, identity property will not be satisfied, I think, because it is
Which one you guess that that could be an identity element and that is not within positive rational number?
No, identity, if 0 is the
Th-
identity element.
So you are multiplying it, right? So do you think that half into 0 equal to 0 into half will give you back half?
No, sir, it will give 0.
0. Then not only that, it's a positive rational number, so 0 is also not here.
Okay,
So
then 1.
okay, so half into 1 equal to 1 into half equal to half. So do you think that 1 is the identity element of this?
Yes, sir.
Yes. So the problem that you had with identity was gone. So identity is
Yes.
there. Then inverse is there.
Sir, as 0 is not
Inverse.
there, sir, I think it is a group.
Yes.
Yes, 0 inverse
So
property is the
this
problem.
is true.
It is a group because 0 is not there. If 0 would have been present, then it would have been invalid.
Yes.
Mm.
Perfect. So that way, by similar argument, you can talk about G star. That means Q minus 0 with respect to multiplication. That is also a group, right? By similar argument. So you might have, say, half. What is the inverse of minus half? What is the inverse of minus half in here in set of all non-zero rational numbers?
-2.
Yes, minus 2, and that becomes 1. So that is a group. Very good. Now what's about R with respect to dot? Real number with respect to dot. Is it a group? True or false? All real numbers with respect to dot. True or false?
So false.
Why?
Inverse element will not be there
Who's
because
in
if
who's
in case
inverse?
of 0,
Yes.
in,
Yes.
ca- in case of
It's
0,
satisfying for all except for 0.
Yes, sir.
So you can understand that all the properties are satisfied except for inverse of 0. And all the properties are satisfied. So why not then r minus 0 and with respect to dot? Will that be a group? True or false?
Yes, sir, it is group.
It's a group.
Yes.
So now you get a bit idea about field. So now you can try to understand that it was almost a group except for r minus 0. And when I talked about field, what I talked, a plus dot, and all the properties are satisfied in this. So that should also be a group. That's why that is the motivation why I am deleting identity element from f with respect to multiplication. So that I will come to you later on. But it gives you a kind of hint that okay, to have a field, not all the properties are satisfied. With respect to, it may not be the case that with respect to this is a group and with respect to this is also a group, also a group. So that is not satisfied. So you have to sacrifice somewhere. That's why you have to put r minus 0 with respect to dot. That is also a group. But it's not the case that r with respect to dot, that is also a group. Okay, that I am coming afterwards. But before going to that, let me have a quick look up few of the important terms. First one is commutative group or abelian group. Commutative group, or another name is abelian group. Okay, so what does it mean? First of all, G star has to be a group with the property that for all AB belongs to G, A star B equal to B star A. Very simple. What does it mean? Suppose I consider Z plus. As I mentioned, it's a group Now take 2 plus 3 and that is same as 3 plus 2. That means you can interchange without any fear. Okay, then that group is called a commutative group. And if it happens for all the elements, it should be true for all the elements, then only I call this group as a commutative group or abelian group. Okay, so let us have a look at another important group, that is symmetric group, say S3. This is nothing but all permutations. So if I ask you the question on 3 elements, how many permutations that you can have? Suppose you have 3 elements, 1, 2, 3, and I want to find all permutations from 1, 2, 3 to 1, 2, 3. How many such permutations are there? Quickly, anybody? How many permutations that you can have from 1, 2, 3 on a set 1, 2, 3? That means how many bijective mappings that you can construct on this set? How many bijective mapping? Okay, let's have a look. So here what I need a bijective mapping. You remember what is bijective mapping? That is injective as well as surjective. So here 1, 2, 3, 1, 2, 3. So I need to have both the properties. So I want actually bijective mapping. What does it mean? It means if and only if it is injective and surjective. So what does it mean injective means? That means if A not equal to B, that implies FA not equal to FB. A not equal to B implies FA not equal to FB. And what does it surjective means? Surjective means, say f is a function from A to B, okay, then I call it surjective if for every say B belongs to, say this is B and this is A, for every B there must exist some A here. So for each B belongs to B, there exists some A belongs to A such that FA equal to B. That means, okay, let me give an example, then it will be easier for you to understand. Okay, let us consider very simple example. Say this is my Z set of all integers and this is my Z set of all integers. I have given a function f defined by fx equal to 2x for all x belongs to Z. Okay. Now, what I said about injective mapping? Injective mappings means if you take any two distinct elements, their image should also be distinct. Say take any element, say 1 and 2, what would be the image here? The image of 1 will be 2 and the image of 2 will be 4 and they are distinct. Okay. So that is true for all AB belongs to this. So this is injective. And what does this surjective means? Surjective means take any element from here, from Z, from right hand side, take any element. There must be some element here as well on which if you put F, that will give you this element. For example, take any element B from here, there must exist some A such that FA should be B. If I ask you this question, is the function surjective defined by this from Z to Z? Is it surjective?
No, sir.
Why not?
So
Very good.
one wouldn't have an image.
So if I consider B to be 1, then you can understand that there exists no such A from here such that f of A should be equal to 1, because it is always giving you some even integers. So there exists no A belongs to Z such that fa equal to 1. As a result, Here, this F is not surjective, right? Okay. Now, if I simply change a bit, if I consider, say, Z, and here it is 2Z, F defined by Fx equal to 2x, the same mapping, I just changed this Z. Previously, it was my Z. Now, I have changed it to 2Z, okay? And the same question, is it bijective? Question, is F a bijective mapping? That means both injective and surjective. What is your conclusion? True or false?
Yes, sir, true.
Okay, somebody says true, and you are right. Why this is true? This is injective, of course. If I take two distinct elements, then suddenly, so let A not equal to B, that will imply, say, 2A not equal to 2B. That imply FA not equal to FB. Fine. But here, since instead I have removed Z part, I just considered only the even integer. For here, any element is an even integer, and for that even integer, you will suddenly get some element here, out of which if you apply F on that element, then suddenly you will get B. That means for all B belongs to 2Z, I mean for each B, not all, for each B belongs to 2Z, there exists some A belongs to Z such that F of A equal to B. As a result, this is a bijective mapping. Clear? Now, suppose I have here a set like 1, 2, 3, and here I have also 1, 2, 3. And I want to define a mapping. A mapping means you have to define for each element here. Suppose this is my set A, so this is same set as A, and F is my mapping. Can you give me a mapping which is bijective? So what I need to do, I need to just define where this F goes. Can anybody tell me an example of a mapping which is bijective? So F1 goes
1 to 1, 2 to 2, and 3 to 3. It will be both surjective and injective.
very good. So if you consider 1 goes to 1, 2 goes to 2, 3 goes to 3, you can see that all the properties are satisfied. Very good. Can you find, I'll write it F1, say, okay. Can you give me another function, F2, 1, 2, 3, which is also bijective? Which is also bijective? Quickly. Any other function? Quickly. I mean, it's very easy. 1 goes to where? Where do you want to put? Say 1 goes to 2, 2 goes to 3, 3 goes to 1. Then that is also a bijective mapping. Okay. Anything? Anything? Quickly.
3 to
1 goes
1.
to 3, 2 goes to 1, and 3 goes to 1, 3 goes to 2.
Sorry, could you please repeat
1
once
goes
again?
to 3,
So just write column wise, tell me. That would be easier. Yeah. What?
3, 3,
3,
1, 2.
3,
1,
1, 2.
2.
Very good. So anything else?
3 to 1.
3, 2, 1. Anything else?
Many, sir. Even
1,
1,
3,
3,
2.
2.
F5, F5, 2, 3. Yes, what?
1, 3, 2.
1, 3, 2. Very good. Anything else?
2, 1, 3. 2, 1.
2, 1, 3. Anything else? Anything else? Yes, you're right, because there is no such extra. So altogether that you can have, all the permutation is only this 6. And that was the question that just now I asked. How many permutations are there or bijective mappings are there from 1 to 3 to 1 to 3? Okay, the answer is 6, and you could find all such 6. And this could be written in a simpler way like this notation. So this row corresponds to this column, and this column is correspond to this row 1, 2, 3. Okay, so now tell me what should be this? What should I write here row wise?
2,
2,
3,
3,
1.
1.
2, 3, 1. Very good. And then this is 1, 2, 3, 3, 1, 2, and then 1, 2, 3, 3, 2, 1, and then 1, 2, 3, 1, 3, 2, then 1, 2, 3, 2, 1, 3. Okay, there is another way of writing in a simpler way. So here see 1 goes to 1, 2 goes to 2, 3 goes to 3, and that element we call it identity element. Okay, now here I will write it in a cyclic notation, and that is also very important. For most of the problems we usually use cyclic notation. What does it mean? So start with 1 and check whether 1 goes to, except for 1, to any other position. So 1, it goes to 2, so I write it 2. Then I check where 2 goes. 2 goes to 3, I write it 3. And then I check where 3 goes, and we can see that 3 goes to 1. So 3 goes to 1. As a result, the cycle is closed. Okay. Similarly, here, can you tell me what would be this? 1 goes
1,
to
3, 2.
3, and then
3
3
goes to
goes
2.
to 2, and then 2 goes to 1. So here 1 goes to 3, and then 3 goes to 1. So it's closed. And you see that 2 goes to 2. If something goes to that position, we do not write it. Like here, 1 goes to 1, 2 goes to 2, 3 goes to 2, 3. That's why we haven't written anything here. Similarly, can you tell me what should be this?
2, 3.
2, 3. Very good. And there, here,
1, 2.
1, 2. Very good. So here you can see that there exist 6 elements, and I started with here 3 elements, here 3 elements, right? So I actually constructed all bijective mappings from here to here. Now can anybody tell me very quickly, if I start with say 1, 2, 3, 4, and if I have 1, 2, 3, 4, then how many such bijective mappings that I could have? Without calculating this, can anybody tell me how many? Okay,
4 factorial.
yes. So that is 4 factorial. So this 6 came because of it was 3 factorial. And this came because this is 4 factorial, and that value is 24. Okay. So, you remember now these elements. Now I come to little bit of abstract algebra with this bijective mapping. So consider all such elements on 3 elements permutation, like E. If you remember, it was 1, 2, 3, then 1, 3, 2, and then 2 cycles 1, 2, 1, 3, and 2, 3. So they are the 6 elements. If you remember, it may be in some different ordering, but all the elements are the same. So if you remember here, see this, they are the 3 cycles. This is the 3 cycle, and then first 1, 3. So I started with 1, 2, then 1, 3, then 2, 3. More symmetrical way, more systematic way I wrote. Okay. So they are the all 6 elements of a set, and I call this set as S3. So S3 is a set. Now I want to define some binary operation on it. I call it composition. How do I define this composition? Let us check. So what you understand that all of them, they are basically a bijective mapping. So you can think of this is F, say this is G, right? So when you write F compose G of X, most intuitively, what you write it here? How do you express this F compose G of X? How do you write?
F of G of X.
F of G of X. Very good. So what does it mean when you, so if I write it like this, so F was a mapping from, say this is A, again this is A, again say this is A. So F was a mapping from A to A, the G was also a mapping from A to A. So when I evaluated F composition G, it starts from where? More efficiently, if I write like this, A, B, C, three different names. In my case, permutation, all ABCs are A. But if I write it in this way, then it would be easier for you to understand. So F is a function from A to B, and G is a function from, say, B to C, right? Now, when I write F composition G, first of all, we need to check whether that is really possible to make a composition or not. So it should be some x. Now the question is, this x should come from where? It should come from A, it should come from B, or it should come from C. From where this comes from? This should come from?
C.
No, this x. Because
Okay.
first you are actually trying to follow this
Okay,
formula,
this
right?
A sir.
It should come from A, but picture wise, if you can see that picture wise, it should be G of X, and G, the X should come from B.
B.
Okay, but as you understand, it should come from A, because this composition should be from A to C ultimately. As a result, if I draw like this, then it won't be the case. Instead, if I interchange this, like if I put G here and put F here, and let's check what is the case. Like F compose G of X. Okay, so G, it starts from A, right? And F, it starts from B. I have already changed. Now this is means F of G of X. Now you can understand, if I have, so this is already changed. So now this is my G and this is my F and this is my X. So if I start from here, G of X, that means G of X should be here, right? And then if I can apply F on it, then I will have F of G of X. So ultimately, this is F compose G is a mapping from where to where? Quickly tell me. Now this F compose G is a mapping from where to where? From A to C.
C.
Yes, because G, it takes element from A, G takes element from A, it goes to B, and then F is applied, ultimately goes to C. So ultimately, this mapping is a mapping from A to C. Clear? Okay. So now, if I have these two elements, say F and G, so 1, 2, 3, composition 1, 3, 2. So the question is, how do I define this? How it should be a natural way. So if I write it in a full, it was like 1 goes to 2, 2 goes to 3, 3 goes to 1. So this is equivalent to this, and this is equivalent. Quickly tell me, 1, 2, 3,
One
where
goes
should
one
2,
goes to
3,
3,
3
2 goes
goes
to
to
1,
2 goes to 1, 3 goes to
3 goes to 2.
2.
2.
Very good. Okay. So this is your F and this is your G. and you want to evaluate on 1, 2, 3. Okay, so tell me which part should I operate first? From here I start, or from here I should start? Try to understand, or try to,
From G first.
yes, that means from here, from this permutation I should take the initiative from here. So here 1 goes to 3, 1 goes to 3, and then I apply F, and here I see that 3 goes to 1, right? So ultimately 1 goes to 1. Again I am repeating, 1 goes to 3 on the right side, because I follow this rule. So here right hand side is G. So I first follow 1 goes to 3 and then check where this 3 goes. And here I see that 3 goes to 1. So as a result, started with 1, it ultimately goes to 1. So 1 goes to 1. Now check with 2. 2 goes to 1 and 1 goes to 2. So this goes to 2.
2.
And 3 goes to 2 and 2 goes to 3. That means 3 goes to 3. That means this is E. Clear? So it was your E. E was 1 goes to 1, 2 goes to 2, 3 goes to 3. Is it clear to all of you? Now tell me,
Yes,
is
sir.
it
Yes,
clear?
sir.
Okay, now tell me quickly what is, say, 1, 2, 3 composition 1, 2. Quickly. Now you can see that from here you can directly do 1 goes to 2 and check where 2 goes to 3. So ultimately 1 goes to 3. So here 3 is absent. That means 3 goes to 3, 3 goes to 3, and 3 goes to 1. That means ultimately 3 goes to 1. So cycle is complete. So also check where 2 goes. 2 goes to 1 and 1 goes to 2. That means 2 goes to 2. That's why nothing is required to write. So ultimately 1, 3. Is it clear?
Yes, sir.
Okay, now tell me what is this value quickly. What should be the answer quickly?
Sir,
So
1,
one,
3.
okay, let's check. 1 goes to 2 and 2 goes to 1. That means 1 goes to 1. So we do not
One.
need to write 1. Let's see, 2 goes to 3 and here 3 goes to 3. That means 2 goes to 3. Check with 3. 3 goes to 1 and 1 goes to 2. That means 3 goes to 2. That's why the cycle is closed. That means it's not still clear to all of you. Okay, let's do it 1, 3 quickly. Start with this. So 1 goes to 3 and here 3 goes to 3. That means 1 goes to 3. 3 goes to 1 and 1 goes to 2. So 3 goes to 2. So here 2 goes to 2. 2 goes to 2 and 2 goes to 1. That's why 2 goes to 1, cycle is closed. Is it clear to all of you now?
Sir, can you please repeat the last one?
Okay. So start with this. 1 goes to 3, right? And you need to check where 3 goes to where. Here 3 is absent. That means 3 goes to 3. So
Yes.
starting with 1 goes to 3 and then 3 goes to 3, that means ultimately 1 goes to 3. Then check with where 3 goes. Here 3 goes to 1 and here 1 goes to 2. That means ultimately 3 goes to 2. So 3 goes to 2. Then 2. Here 2 goes to 2 and here 2 goes to 1. That's why ultimately 2 goes to 1. Since it's coming back to 1, the cycle is closed. Is it clear?
Yes.
Yes, sir.
Okay. So now it can be shown very easily that with respect to this my composition, it forms a group. Okay. So it satisfied all the properties. If you make composition of any two elements, then it should be within S3. It is associative. What would be the identity element of this? Can anybody tell me
One,
what?
1, 2, 3, 1, 2, 3.
Yes, exactly. And you can check that here. This was your, so where was 1 2 3? So just now we have seen that this was E, right? So the inverse of this is this, and the inverse of this is this. And for two cycles, and that can be very interesting properties. So if you are really interested on this, because they are very basic mathematics, I am now giving a course on group theory. In my YouTube video, you can just have a look at the first 4 maybe classes on group theory. Then all the binary composition, all the operations, all the equivalence relations, everything I mark with detailed. So if you are interested in, you can just have a look at the initial 4 classes on group theory, the course, and everything will be quite clear. So there we geometrical interpretation, how geometrically it should look like, what is the relation between an equilateral triangle and S3, how geometrically they will look like, everything was given in detail. So you will also get some mathematical intuitive idea how they actually develop. So actually this Sn, this group S3, S4, S5, this group came actually much earlier than the original definition that we are currently studying, the axiometric definition, much before they were studied. So many of the important theorems of group theory, like Lagrange's theorem, many theorems like Abelian group. So you may think of that Abel might have given the name Abelian group, but it was not the case. When Abel was there at that time, the axiometric definition, he didn't know anything about group theory formal definition, but the name actually given after his name. So Abel didn't have much idea about the axiometric definition, but now I'm going to give you what do you mean by the Abelian group. So just now we have mentioned that Abelian group or commutative group means A composition B should be equal to B composition A for all A B belongs to G. That means you can commute. For example, Z plus is a commutative group. So it's a commutative group 2 plus 3 same as 3 plus 2. Similarly, if I consider Q star dot, that is also commutative, say half into 3 is same as 3 into half. Doesn't matter. So they are examples of commutative groups. If I ask you the question, is S3 a commutative group? What would be your answer? You have already done. True or false? Within the screen you
False,
can.
sir.
Why false?
1, 2, 3, and
Yes,
1, 2 will give 1, 3, but
exactly. So due to this result, so if I consider AB and this is my BA, then they are not same. Okay. So as a result, this is a commutative group. The answer should be false. Okay. So now you understand the concept of commutative group. So if you are within a commutative group range, then you can freely interchange, switch the operations. So that is very important. That's why we need this kind of concepts for group theory. That if something is within our range, and then if we can interchange the elements, then it would be easier for us to communicate. So that give you more free property. That means you are quite free to switch or interchange the elements. in with respect to this operation, then that will give you more flexibility. So that's why commutative group is very important. Okay. Now I'm going to give you another very important example that is widely used in cryptography. So just now we have already seen the idea of say Z. Z we have already seen. So this is, if I write it geometrically, then you can think of this is a line. This is a line, and say uh, with 0 here, then this is say 1, this is your 2, this is your 3, this is your 4, this is your 5, and so on. Here also we'll have -1, -2, -3, -4, -5, and so on. So this is an infinite line. Okay. Now, just now we have seen that Z plus is a group, is a, more importantly, is a commutative group. Commutative group. Okay. Now, this is an infinite commutative group because this contains infinitely many elements. So this is infinite. But being a student of IT or computer science, you understand that it's really difficult for a computer to achieve this infiniteness. So if something is infinite, then for computers, it's really difficult to achieve the concept of infinity. Okay. So we certainly require some finite cases or finite number of steps we need to go, or we need to deal with some finite many elements. That's why people thought in a different way. Okay. Take any integer n which is greater than 1. For example, take n equal to 5. Okay. And then divide all the elements that you have with 5. So I will have a bucket which I call a bucket which has remainder 0. When you divide by 5 all integers, you collect all the integers within this whose remainder is 0 when that is divisible by 5. For example, 0 should be here, plus minus 5 should be here, plus minus 10 should be here, plus minus 15 should be here, 20, 30, and so on. So this bucket consists of infinitely many integers, maybe positive, maybe negative, and also 0. Now, if I ask you this question, what this bucket will contain, give me some example that integers should be within this bucket. Quickly, some element, some integers within this bucket.
Within this bucket means remainder will be 1.
Remainder will be 1. Yes.
So 1 plus minus 6 plus minus
Okay.
11.
Okay, let's see. 6. Now the concept again, in my class I have already mentioned you what is minus 6. If I divide it by 5, what should be the remainder and what should be the quotient? Quickly tell me. What should be the quotient and what should be the remainder? Then again it will be a problem of division, and it would be difficult for you, all of you, if you won't be able to give me the answer quickly. Then you may have to sit with your cousin or your nephew maybe to understand division properly. So what would be quotient and what would be the remainder? Quickly tell me. Oh, it's taking too much time. Tell me. If I divide 5,
Quotient will be -2 and remainder will be 4.
so this will be minus 10. So this will be plus, and that becomes 4. Yes. So minus 6 will be written as 5 into minus 2 plus 4. That's why the remainder should be, mind that the remainder should be, so if I have a and b, two integers with b not equal to 0, then there exists quotient and remainder belongs to z, such that if I divide with by b, then a should be written as bq plus r. Most important part is this: r should be strictly less than mod of b. Sometimes people forget to write this mod of b, and if you forget this, then you might have different answers for a simple division. So as you understand, if I have minus 6, then minus 6 should come here and not here. Okay. So similarly, in with respect to minus, which element will come here? Quickly tell me which element should come here. Which element should come here?
-9.
Minus.
9.
Okay. Minus 9. Anything before that, you could have also minus 4, right?
Yeah, -4.
Now you can increase by 5. That would be fine. 1 plus 5 is 6. Then 6 plus 5 is 11. Here also, if I have minus 4 plus minus 5, then that becomes minus 9. Then minus 9 becomes minus 14, and so on. Okay. Now you can understand what are the things here. Here 2, 7, then minus 3 will come here, and then minus, what would be next? Minus 8,
8.
then minus 13, and so on. So here 3, then 8, then maybe 13. And in case of minus, it should be minus 2,
2.
minus 7, minus 12, and so on. Similarly, here it would be minus 6, 4, then 11, sorry, 4, and then 9. And then in case of minus, it would be minus 1, minus 6, and then minus 11, and so on. Okay. So that are the elements. So you can understand that if it is again 5, then it will go here. Okay. So even if there are infinitely many such integers, if I divide it like this, then I will have only 4 buckets with only 5 buckets with remainders 0, 1, 2, 3, and 4. So 1, 2, 3, 4, 5. So 5 buckets with remainders 0, 1, 2, 3, and 4. And each of these buckets will contain infinitely many such elements. Now, from each of this bucket, you can choose a leader. For example, you can choose 0 to be a leader of this set, and sometimes we write it like this. Some of the authors, they write a cap on it because they are leaders. Okay. So you can write like this, 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 and consider a set. Okay. And this set is known as addition modulo 5. That means consider z and then modulo it with by 5. Consider all the representatives from each of these buckets and take the collection. So I have a set. Now for algebraists, having only a set, they are not that satisfied. So what they need some operation. So okay, let us put some addition. So now how this addition is defined. Okay. For example, take any element, say from bucket this. From bucket element, take any element from this bucket, say quickly, tell any element from here. Take any
6,
element from here.
6 minus 9.
Okay, say minus 9, one element. And say take any element from here. From here, any element, take
8.
8. Very good. Now add them up. Normal integer add. Minus 9 plus 8, that becomes minus 1. And check minus 1 is in which bucket. So
4.
they are the bucket for this is the bucket for 0 bucket. This is the bucket for 1 bucket. This is the bucket for 2. this is the bucket for 3, and this is the bucket for 4. And it has been found that this is within the bucket 4, right? Now, consider the leader of that bucket from where -9 belongs. Okay, -9 belongs to the bucket of with leader 1. So add 1 plus, you have taken 8 and the leader was 3. And that surprisingly gives the same result, 4. And this -1 belongs to this 4. That means instead of disturbing each of these elements from this bucket, it is sufficient to consider only the leaders and define the addition among the leaders, and that will be all. So instead of considering any element, so basically that is a leader of a party, and this party, there exists infinitely many party members of this. Similarly, there exists infinitely many party members of this. But to add them up, it is sufficient to consider the leaders only. For example, if I add them up, for example, 3 and 4. So 3 class plus 4 class, that becomes class 7. And let's see where the 7 belongs to. And 7 belongs to 2. So we call it 2 class. That means just simply 3 plus 4 and then modulo 5, and that gives you 2. So that's all. So if I add this as like this, that means take 2 elements from this set, just add them up, and then after adding whatever integer you will have, just consider this. That means it is nothing but class A plus class B should be equal to class A plus B. So this means actually A already by 5, this means B remainder 5, and this means A plus B there 5. Now it's clear to all of you. So
Yes, sir.
if I consider this, then it can be also shown that Z5 with respect to the addition as just now I have defined like this is a group. Okay. Now my question is this a commutative group? If I ask you the question, is Z5 plus a commutative group? What is your intuition, true or false?
True.
Yes.
True.
So it's easy to check that it is true. It's a commutative group. But it has a very special property that many of the groups do not have. For example, if I consider, so now you can understand what could be Zn plus. So instead of 5, you need to divide it by n and then take the remainder. That will be all. Okay. So what is then special properties of Z5 plus, or in fact any Zn? So if I consider this, like the elements here are class 0, class 1, class 2, class 3, and class 4. Okay. Now it has a special property that if I consider class 1, okay, and if I, so addition is the operation here, and if I apply the addition only once, I mean, if I do not apply the addition, I will get this element. If I add 1 plus 1, I will get class 2. So I get this element. If I add 1 plus 1 plus 1 3 times, I get basically this element. If I have 1 plus 1 plus 1 plus 1 4 times, I'll basically get this element. So who is remaining? So 0 is the only element that is left. Let's check. If I add 5 times, 1 plus 1 plus 1 plus 1, 5 times, that becomes 5. And as you remember, 5 means 5 modulo 5. That means 5 having the remainder after division by 5, it becomes 0. So again, I get this element. So this one has a special property that it is capable of generating all the elements, all the remaining elements of the group. That's why this group is called a cyclic group. Cyclic group. So what is a cyclic group? A group having a generator. Having a generator. So what is generator? A generator is an element which is capable of generating all the remaining elements of the group. Is it clear? What does it mean generating? For addition, you can understand that by adding them up, all the remaining elements, if I able to generate. That's why. So it has at least one generator. Now my question is class 2 a generator? Is class 2 a generator of Z5? Is class 2 a generator of Z5? So class 2 can generate class 2. If I add class 2 plus class 2, what I'll get? I'll get class 4. If I add 3 times, I will get class 6 means class 1.
1.
Then if I
Then
consider,
we can also get class 3 because we'll get 8, and then again
yes,
0 because we'll get 10.
yes. So class 2 is again a generator. Now my question is class 3 a generator? Quickly.
So we'll get 3, then we'll get 1 because 6,
Yeah.
then 9, that means we'll get 4, then 15, 0, 21 also we'll get. So yeah, it can.
Okay, so we see that 1 is a generator, 2 is a generator, 3 is a generator. Will 4 be a generator?
Yes, sir.
Yes, 4 is also a generator. Is 0 a generator?
No.
No.
So you see that in Z5, except for 0, all elements are generator. Okay. Now that's quite amazing. So that means it's a cyclic group in a bigger sense. All the non-zero elements are generated. What I say, a cyclic group means it should have at least one generator is sufficient. But you see that there are plenty of such generators. Now let's again have a look at another group. For example, let's Z6 plus. Okay. So is class 1 a generator? So elements I can write like this. Is class 1 a generator?
Yes.
Okay, then is class 2 a generator? So it's already a generator, class 1. What's about class 2? So if you start with, I'm not writing a bracket. So if you start with 2, then adding up 4, adding up 0, then again adding up 2, 4,
Yes,
0,
sir, not a
2,
generator.
4, 0. So not all the elements can be generated from here. So this is not a generator. What's about 3?
3, 0, then 9.
3, 0, then 3.
3.
Mind that we are considering it
Yes, sir. Yes,
Z6.
sir. Yes, sir.
So
Then it will
0,
15, 0. Yeah.
so this is also not a generator. Oh, what's going on? Then class 4. So 4,
2,
then 2, then 0, then
0,
4, 2,
4, 4,
0.
2, 0. Yeah.
Oh, what is your last hope? Let's see. Will 5 be a generator? Let's see. 5.
Then
Then
4.
10 means 4.
4.
Then 9. 10 plus 5, 9 means 3. 3 plus 5 means 8. 8 means 2. 2 plus 5 means 7. 7 means 1. 7 plus 5 means 12. That is 0. So it's giving 0, 1, 2, 3, 4, 5. All the elements. So here it's quite unusual I mean, unlike the last case. So in my last case, it was like this, and here we have seen that 0 was not, but 1, 2, 3, and 4, all of them, they were generators. But here something mysterious happening. In Z6, 1 and 5 are the only generators of Z5. Now if I ask you the question, just having this, looking at this pattern, can anybody tell me what could be the generator for Z10? Quickly. Having, you must find some pattern here. So in cryptography course, always we need to try some, while attacking something, we always try to find some kind of patterns here. Is any pattern that you can find?
1 and 9.
Okay, somebody says 1 and 9. Very good. One pattern she has already found. Anything else? So you say that 1 or 9 are the only generators?
Sir, maybe 1, 2, 3, 4, and 6, 7, 8, 9.
Okay, but if you consider set 2, 2 was one of your generator, right? So if you
Yes, sir.
consider 2, then 4, then 6, then 8, then 0, then again 2, 4,
2, 4,
6,
6, 8.
8.
They are not, will not work.
So 2 cannot be, right? Let's start with 3. Then 3, 6, 9, then 12, 2, then 5, then 8, then 11. 11 means once, then 4, then again 9. 4 and then again uh, so 4, then 7. 7, 10, 0. Is all the elements exhausted? 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. So you can see that 3 is the generator here. So the first answer that I get, 1 and 9 are the generators, among which 3 is also a generator. Now I think it would be quite clearer to all of you what should be next.
5.
Who should, why? So what is the specialty?
7.
Yes, 7. And then that's all. See, 6 and 1 is relatively prime. 6 and 5 is relatively prime. That's why relatively prime means GCD of 6 and 5 is 1. GCD of 6 and 1 is 1. Here GCD of 5 and 1 is 1. 5 and 2 is 1. 5 and 3 is 1. 5 and 4 is 1. So in short, if I write like this, ZP plus, where P is my prime. If I ask you the question, how many generators? How many generators? What would be your answer? If P is a prime, then how many generators? Think about this. 5. How many? 4.
P minus 1.
P minus 1.
Yes. P minus 1. So there should be P minus 1 many generators for this. Okay. Now, if I ask you a little more, what, how many number of generators of, say, 49 class? Then you have to calculate, okay, who are the numbers who are relatively prime to them. And for the sake of simplicity, if I consider, say, 101 was a prime, then if I give only 101, then it would be easier for you to give me the answer P minus 1 means 100. But for the sake of simplicity, if I consider like this, how many generators are there for a group of order 101 to the power 2? That means 101 square. with respect to plus, then you will be stuck. But mathematics plays an important role here, and it's also very important for number theory. Okay, do you require this page, or shall I? I mean, I am now okay. I have some more pages there. Okay, some more space is there, so I will still have some more page. Okay, maybe one page kind of. Okay, so there is a concept. So what was my question? How many generators are there in this group? Say 101. Sorry, put like this 101 with respect to addition. So this group contains 101 squares many any. So you need to find basically the number of elements which are relatively prime to all such 1, 2, up to 101 square. So it's too big. But here mathematics comes into play. You can write a program, but whatever that I am going to give you will give you a quick answer, more efficient way of giving the answer if you even if you write an program. So you might have heard about Euler Phi function, phi of n. This is called Euler Phi function. You remember Euler Phi function, where n is greater than equal to 1. This is nothing but exactly what we are searching for. That is number of positive integers less than equal to n and relatively prime to n. Relatively prime to n. That means those numbers which are within the range 1 less than equal to x less than equal to n, such that this x and n, GCD of this x and n equal to 1. We are actually trying to find that many numbers which are relatively prime with 101 square. So here n is my 101 square. So we are trying to find that many x, right? So is there any simple way of doing that? Okay, so already you have seen that if p is my prime, then what is phi of p? Quickly, what is phi of p?
P minus 1.
P minus 1 if p is prime. Very good. Now, if I ask you what is p to the power n, where n is greater than equal to 1. Okay, so we need to count that. Okay, how to count this? So what actually phi of p to the power n? It's all such, we are actually trying to count all such x such that 1 less than equal to x less than equal to p to the power n and GCD of x and p to the power n equal to 1, right? So that cardinality, so this is the set, and how many elements are there within that set is basically my p to the power n of phi. Okay, okay. Now if I ask you the question in a different way, that try to find the numbers, how many elements are there within this range which are not relatively prime with p to the power n. That means suppose I consider another set, say y, such that 1 less than equal to y less than equal to p to the power n and GCD of y and p to the power n, it was 1 and I want not equal to 1, and I need to find this cardinality. Okay, so what is the speciality of this y? Can you anybody tell me what is the speciality of this y with respect to the prime p? Remember, the GCD of y and p to the power n is not equal to 1 and p is a prime. So what is a speciality of y? Can anybody tell me what is some speciality of y with respect to that p such that GCD is not equal to 1? Since P is prime, so Y must be of this form. Y must contain P as a factor. That's why they are not relatively prime. So Y must be of this form, P into some Z, where 1 less than equal to Z. And what should I write here? Z value. What should be the Z value, maximum value of Z? What should be the maximum value of Z? It's P to the power n minus 1. So you understand that this cardinality will be, it depends on Z. How many Z you get? You will get basically P to the power n minus 1 such Z. So that is P to the power n minus 1. So these all are elements which are not relatively prime with P to the power n. So you had, so phi of P to the power n, that value should be, you had initially total P to the power n many such integers. So from here to here, how many integers are there? P to the power n many integers, out of which they are not relatively prime. So how many are there who are relatively prime? That minus P to the power n minus 1. So this is the value of phi of P to the power n minus 1. So now you can very easily calculate what would be the phi of, that means how many generators of Z101 square is there. The equivalent to find phi of 101 square. And that just now what we have seen, this formula is phi to the power n minus, so that is P to the power, P here is this square minus n minus 1, that means 101. That is nothing but 101. If I take common, 101 minus 1, and that becomes 100. So 10100. So this is the answer. Is it clear to all of you? So that way Euler Phi function plays an important role. Another very interesting property regarding Euler Phi function is that, okay, is this part is clear to all of you?
Yes, sir.
So you just need to remember this formula. This is very important. Again, when we are study many times like RSA crypto system, then this Euler Phi function will play an important role. And next property is going to also very important. What it says, if GCD of AB equal to 1, then phi of AB equal to phi of A into phi of B. That means it is called multiplicative property. Multiplicative property. So it says that if GCD of AB equal to 1, then phi of AB equal to phi A into phi B. What is the importance of this formula? For example, if I ask you the question, what is phi of 100? Now you can understand that you can easily break it into prime factorization. And this, if I consider this to be A and this to be B, then 4 and 25 are relatively prime. So phi of 2 square into phi of 5 square. Now you know the formula for P square, right? So what is that formula? 2 to the power n minus 2 to the power n minus 1. And this one, 5 square minus 5 to the power 1. And that gives you the result 2 into 20. And that gives you 40. So that's the important. So now you can understand what should be the value of maybe say 1000. You can very easily do that. What should be the value of 1000? Very quickly, somebody. How to do that? So 100 is already there. Only you need to multiply with 10. That's why it should be phi of 2 cube into 5 cube. That's all. and that is pi of 2 cube, pi of 5 cube, and that gives you 2 cube minus 2 square, 5 cube minus 5 square. Okay, something like that. You check what is this value, 400 or not. Okay, so this is 8 minus 4, that means it becomes 4, and this is 100, so it's equal to 400. Very good. Now you can understand what is the power of this. So that's why I have first made a term like pi of p to the power n, and I know that any integer can be broken in terms of prime products, and that is known as fundamental theorem of arithmetic. So in fundamental theorem of arithmetic says that any positive integer can be broken in terms of product of primes. Any positive integer greater than 1. You can write always in terms of product of primes. And if I consider this separately, they are all relatively prime. So you can break it up with maybe a product of 3 numbers. Then also you can do the same way. So Euler Phi function plays an important role. Okay. Now, another two important things are important here, that is known as Fermat's. Okay, so before that, let me go to another thing. So we have seen that Zn plus is a cyclic group. Cyclic group, no doubt about that. If I now consider is Zn with respect to dot as a group, what is your claim? True or false? Zn with respect to dot, is it a group? True or false? What is your claim?
True.
Okay, somebody says true. You can see that all the properties almost satisfied. Now tell me what is the inverse of 0. So that what is the inverse of 0? Or tell me what is the identity element of this? What is the identity element? First, let
1.
me, 1 is the identity element, right? Now tell me what should be the
Doesn't
inverse
satisfy.
of,
Like 1 into 0 gives me 0 only.
yes. So you never have the multiplicative identity of 0. So this is not a group. So this is false, right? Now, so as just now we have seen that if I remove the 0 and if I consider dot, will that be a group?
Yes, sir.
So true or false? Your bit is on true, right? Okay, let us consider. So Z6
But it will
plus,
again generate 0. Like
yeah,
because
I
we are
don't have
having a
0.
cyclic group.
No, so I'm just asking you whether this is a group or not. Not even asking you whether this is a cyclic group or not. Just a basic question, is it a group or not? So my question is, if I remove 0 element from Z6, will that be a group? Because just now we have seen that 0 was a problem. Now we just remove the problematic part and ask you the question whether that is a group or not. So what is your intuition? You tell that this is a group. Let's see. What is the multiplicative inverse? So here also the identity element would be 1. That is for sure. If that would be a group, then 1 should be a multiplicative identity. Now, if I ask you the question, what should be the multiplicative inverse of class 2? What would be the multiplicative inverse of class 2? That means you need to give some class A such that product of which it will be class of 1. Okay, so let's start with 1, then it will be 2. Let's start with 2, then it will be 4. Let's start with 3, then it will be 0. So
But 0
we
is
are,
not present.
0 is not present, as well as we are trying to find something which should be 1. If I multiplied it by 4, then it would be 2. If I multiplied it by 5, then it would be 4. So we have exhausted all the elements here, but still we are yet to get any element product of which will give me 1. So what is your conclusion? 2 will not have
Not,
any inverse.
yes, sir, not a group.
Similarly, which element will not have inverse? 4 will also not have an inverse. You can check. But let's check what would be the inverse of 1. What would be the inverse of 1? That will
1
give
into 1 is 1.
1 is itself.
Yeah, self-inverse.
And what would be the inverse of 5?
For 25, 5.
5 itself. Okay. And what would be the, let's check. So 4 you can check on your own that it cannot have inverse. Let's check what's about 3. What would be the inverse of 3? So start with 1, it would be 3. So if I consider A, and that should be equal to 1. Start with 1, it's 3. Start with 2, it becomes 0. Start with 3, it becomes again 3. 4, it becomes 0. 5 again 3. So you can see that for class 3 as well, it will not have any multiplicative inverse. So 1 is having an inverse, 2 does not have, 3 does not have, 4 does not have, 5 has. So 5 has an inverse. So out of all these elements, we can see that only class 1 and class 5 have the multiplicative inverse. Now can you tell me Z10, which element will have the multiplicative inverse?
1,
Class 1 will certainly have, then class
3,
class
3.
class 3, very good. Class
7.
7. 7, 9.
7, 9. So now you understand that with respect to multiplication, if I need to have the multiplicative inverse, we need to consider all such elements which are relatively prime to n. Okay, and that group is also very important. We call it group of units. Group of units, and that is denoted by Zn star, or somebody denote it by Un. So Zn star or Un with respect to multiplication. Okay. So if I ask you the question, what would be the cardinality of Zn star? What would be the cardinality of Zn star? Quickly tell me. Just now I have given you. So that depends on n. So what function shall I write here? What function shall I write here? So that you can get the answer. Cardinality of, so just now you have seen that Z10 has 4. And what is 10? Which elements are relatively prime to 10? So how many such elements are there? In short, what we'll call? We call it Euler Phi function. So the cardinality of this is phi of n. Okay. And this group plays the most important role in RSA public crypto system. Till now, whatever I told you, it's only about, mostly about groups. So till now, whatever I told you are very important for studying cryptography from group theoretic viewpoint. So I may need one more class to discuss about little more about groups and then a bit about fields. Okay. After that, you will be comfortable with the public key crypto system as well as with the things that I have just in my last two videos. You might have seen that there you have the idea of Sn, you had the idea of Zn, and that's all. And you also had the idea of inverse. When that inverse exists, then you will able to understand that this inverse will exist if and only if GCD of A and n equal to 1. So just now I have given you that idea. So all the things are being required very much in understanding cryptography from a deeper way. So unless you are quite comfortable with this, it would be really difficult for you to learn about public key crypto system from heart. You may implement those things, but how and why they are happening or why they are working, it would be difficult for you to understand. But I think if you just go through any book, you can follow my book, Basic Modern Algebra with Applications from Springer. If you follow that book or any book, standard book, if you follow, there are plenty of very, very good books, and they're like Galleon's book, or Damit Food is there, or Malikshan Moderation. You can study any book, and if you do the basic brush up things, then it would be clear for all of you. Or you can also visit my YouTube channel, for where I am offering the group theory, basic of group theory. If you just read the first 4 to 5 lectures, then that will also be quite clear to all of you. Okay, is there any question?